Hi, everyone. Hey, let's talk a little bit about thermochemistry, thermodynamics, and the energy of reactions. Okay, so here's the deal. Chemical reactions can either give off energy or absorb energy, and we can measure that amount, and we call it something, right? Scientists love putting new names on every new idea. So the amount of energy in the form of heat released or absorbed during a chemical reaction is called entropy, enthalpy. And so we symbolize it with the delta H. It's also known as the heat of reaction. So that's H for heat. You can think of it as being that H there too. That's a good way to remember it. And it turns out, like it's just said, that some reactions release energy, release heat energy, and we call those exothermic. So if you are an exothermic reaction like a fire, fires are exothermic, exothermic reactions, the heat is coming out. So if you are the fire, you're releasing heat energy and kind of shrinking away as you lose energy. Um, the energy is exiting from you. So that's how I remember the term exothermic. There are reactions that release heat energy. And it turns out the value of delta H, the heat of reaction, is negative because from the reaction's point of view, it is releasing energy. So fire gives off heat and light. It's exothermic. And the delta H is then a negative number. There are other reactions that will absorb heat energy. There's some reactions that don't work unless you supply heat energy, and the heat that you're warming up the reaction to make it go, that energy is being absorbed and helping it to convert reactants to products. And so it takes in that energy. And from the reaction's point of view, then energy is coming in or entering it. So these reactions are called endothermic, sort of like entering into them, endothermic reactions. And their value of delta H is positive. It's a net energy gain. It's gaining energy as it absorbs energy and converts reactants to products. Cool. Sometimes students at this point say, well, why is there an energy flow? Why do some reactions give off energy and others absorb energy? Well, if you think about the process of chemical reactions, you're taking reactants, converting them to products. Physically, what does that mean? Well, it means you're taking these reactants and shuffling the atoms to make new molecules. So to do that, you have to take the reactants and break away bonds. That takes energy. So then you can exchange atoms and then reconnect them or remake new bonds. And that actually releases energy. There's a conservation of energy. It says that energy is neither created nor destroyed. So if it takes energy to break a bond, you have to put in energy. It's actually endothermic to break a bond and have two separate atoms. Then if you put them back together, where that energy, the energy that was absorbed to break them apart, when you put them back together, it releases that same quantity of energy to reform the bond. So making a bond is exothermic. Cool. And so simply, some reactions are endothermic, other reactions are exothermic. It just depends on the difference between how much energy is being absorbed to break the bonds versus when you make the products and recombine the bonds, how much energy is being released. And so is there a net gain of energy? Was it more absorbed than released? Then it's endothermic. Or were the bonds pretty unstable? Were they easy to break, like in dynamite? And you made some molecules that are really stable, very strong bonds, and a lot of energy came out. Those are very exothermic reactions. Cool. All right, let's slide this out of the way and go to the next item. Oh, okay, so just some examples. Exothermic reactions. You may have seen these heat packs. You flex them, you break them, you mix them up. Somehow you start a chemical reaction, and then inside these little pads, a chemical reaction takes place that releases heat energy, and Feels pretty good. On a cold day, it warms up. There are other reactions, like if you sprain your ankle, they do the other thing. You shake them up, break something, you mix chemicals inside these packs, ice packs, cold packs, and as you mix chemicals, they're endothermic reactions. They absorb energy. And where does that heat energy come from? Well, it comes from the water that's in these bags, and it comes from you. So as if you put this on your ankle to soothe it after you sprain it, the reaction taking place inside the ice pack is absorbing energy from the water inside these bags, and then that cold water absorbs energy from you and cools you down. Okay, new idea. Spontaneous. Now, this word you've probably heard around in everyday life. Like someone walks in, you're sitting on the couch doing nothing, and they say, "Hey, let's go see the movies." That was before COVID-19 when you could go to the theater, but just spontaneously, just do something creative and something fun. In chemistry or in science, spontaneous refers to things that just happen by themselves. Um, Typically, you have to give them a little kickstart. You have to put a spark to them and make them go, or you have to put in a little initial burst of energy. But after they get started, they can just keep going indefinitely until they run out of reactants. Those are spontaneous reactions. And a very common example is a fire. Once you set something on fire, as long as there's plenty of fuel, more things to burn, it'll keep going all by itself. The reaction continues spontaneously. One little warning, spontaneous does not mean fast. Kind of implies that in real life, but the chemistry definition of spontaneous does not mean fast. It means, does it happen all by itself after it gets started? So on the left side of this diagram, we got some ordinary nails. You leave them out in the rain. A couple days later, they're all covered in rust. That's a spontaneous process. It got started all by itself. It keeps on going. These nails eventually, over a couple of years, are just going to degrade and fall apart as the rust powder falls off. But that's a very slow process. We still call it spontaneous in chemistry. It's continuing to go. It's continuing to rust all by itself. Just needed a little start. Cool. Oh, top of the page over here. Okay, and here's the bottom line. If we're doing some research, or we want to develop a new solar panel with doing some chemistry, or if you want a new fuel cell for the car or something, you might think of some experiments to try to do that. Hey, it'd be really cool to save some time, not have to go in the lab and try every single experiment, see if it works, but write it on paper and then be able to predict, will this reaction run all by itself? Will it be spontaneous or will it not? So here's another example to kind of get the idea down that not every reaction is spontaneous. We got the reaction of a Bunsen burner here. So if you take natural gas, which is primarily methane, CH4, oxygen from the air mixes with that, and with a spark, just give it a little kickstart, spark, you'll start the flame going. And as long as you keep supplying more natural gas in this line, there's lots of air in the room, it'll just burn indefinitely. It'll keep on going. It's spontaneous. It keeps on going all by itself. And the products are carbon dioxide and water. Now, wouldn't it be cool if you could take the carbon dioxide and water and put in some heat energy and reform natural gas and oxygen? That'd be actually kind of cool. Be a great way to make some fuel, methane, and some fresh oxygen to breathe. But this doesn't happen all by itself. You can't just get, a container of carbon dioxide, mix with some water, heat it up. It isn't going to make methane and oxygen gas. It's not, just ain't going to happen. It's not spontaneous. And it's like, well, why not? And then more importantly, how could we have told that's going to be the case without trying it out? Is there a way to predict it? It turns out, well, there's some patterns here. Let's hide this a little bit and get to the main idea. Okay, so some clues. Is it predictable? Well, are there some patterns? Maybe we can just look at some common examples and figure out what spontaneous reactions usually consist of. What's their trend, their pattern? Well, it turns out many exothermic reactions happen to be spontaneous. We already said the fire. There's other things that release heat, and oftentimes those reactions that release heat are exothermic. They happen all by themselves. They're spontaneous, but not everything. There are some endothermic reactions that are spontaneous. A good example is ice melting. So you put a piece of ice on the countertop. We can actually draw the chemical equation for that. You just, drop some ice on the counter or on the floor, come back later. Hey, where's that ice cube go? Oh, it spontaneously formed liquid water. It melted all by itself. And the more ice you throw on the floor, more melts. It just keeps on going all by itself. It is spontaneous. But is melting ice an exothermic or endothermic process? Well, just like we said, be the fire and release the heat. Be the ice cube. You're going to absorb the heat to change solid ice into liquid water. Yeah, so this is endothermic. Melting ice is an endothermic process. It requires an input of heat into the ice to change it into liquid water. Hey, but it's spontaneous. So this is a nice try, but but it's not the answer. We can't simply say, oh, exothermic reactions are all spontaneous. Well, that's not true. But many of them are. So there's something here. Turns out to predict which reactions are spontaneous, you need to know two things. The change in enthalpy, which is delta H. So this actually was a good piece of evidence, good information to have. It helps if your reaction is exothermic. It is quite likely to be spontaneous. But then you don't only look at delta H, exothermic, to decide is it spontaneous. You have to also look at something else called delta S, the change in entropy. It's a measure of molecular disorder or randomness. So a little bit about that first. So if you clean up your house, you wash the dishes, you leave for a couple hours, you come back, it's like, what happened to the kitchen? It's a big mess in here. Things just tend to go from well-ordered, organized to disorder and random. That's just how life is, right? Got a nice vase on the counter, and a couple years later, someone knocks it over and breaks. Hey, now all these little pieces are scattered all over the place. It's more random. Gosh, what else? So the fire. Got some nice logs, neatly stacked. You pull them off, throw them into the fireplace or in the fire pit, make a campfire, and all the smoke rises and goes all over the place. The ashes kind of spread out. Things are much more random. And that's just how life is. That's the way our universe is. And so it turns out that if you have a reaction or a process like melting ice, where things are becoming more random or scattered, nature says, yeah, that's something that will happen spontaneously. So there's the key. If you have exothermic reactions and reactions that become more disordered, they are spontaneous. And then there's other cases, like we said, endothermic. Wait, that means they're not exothermic, they're the opposite. Well, endothermic reactions can still be spontaneous if they create a lot of randomness. Cool. Okay, so you need to consider both. Delta H, the heat of reaction, and delta S, the change in entropy, a measure of increasing disorder or randomness. To kind of keep them apart, because they both start with E, enthalpy, entropy, focus on that H of enthalpy. That helps me remember, oh yeah, enthalpy, the heat of reaction, that's the H. And entropy, S, It's kind of curvy and kind of crazy. Whatever it takes, right, to keep it in your head. Delta S is entropy, the randomness. Okay, it turns out that you can assign a value to the randomness of a reaction and to molecules. If you take more chemistry, we'll get into that in more detail. At this level of chemistry, though, you just need to get a feel for whether things are becoming more or less random. And there are 4 trends you should be aware of. And actually, you probably already are. We'll just reinforce them by going over them. So here's some trends about entropy. And first of all, if we talk about something becoming more random, more disorganized, more messy, we're saying delta S is positive. Delta S entropy is a measure of how random things are. If they're getting more random, it's a bigger number, a bigger positive number. If you're cleaning up the kitchen, everything's nice and clean, all the dirt is separate from all the dishes are dry, no water on them, neatly stacked, everything's neat and ordered, that's low entropy. That's well organized. Not much entropy there. It's a small number. Cool. Okay, so 4 trends. Be aware of these. Gases tend to be much more random than liquids. And liquids tend to be more random than solids. So think about things on a molecular level. So if you have some ice cubes in a flask and you could zoom in and look at the water molecules, what would you see? You would see the water molecules neatly arranged, well organized into these 3-dimensional honeycomb fashioned arrays of water molecules. They're neatly arrayed. Look how many of them have a hydrogen atom pointing up towards us. They're all the same. These right here. There's others that are at the corners and stuff. They're all connecting by hydrogen bonding. And you know what? If you know where one of them is, you got a pretty good idea where you can find the others. Sort of like other spots on this hexagon. Cool. Well ordered. Not random at all. Solids have very low entropy. But you melt this, the ice turns into liquid water, they bounce around, they turn, and they orient themselves in lots of different ways. In this case, over here in the solid, a lot of hydrogens pointing straight up. This water molecule points down. Okay, those two do, but maybe that one, but a lot of them are pointing different ways. There's much more random orientations. And hey, if I know where one is, there might be another one nearby, but is it up, down, left, right? It could be anywhere. Whereas in a neat order arrangement, if you know where you are, you can predict, okay, if I go this way, I'll find another one, go up, go over. Much more order in a solid. Liquid molecules are more disordered. And then if you go from a liquid, where all the molecules are at the bottom of the container, bouncing around in there in the liquid phase, if you heat them up so they're all in the gas phase, well, then they could be anywhere in there with any orientation and going multiple speeds, much more random. So gas is much, much more random than liquids and solids. Cool. So think about the molecules and how neatly ordered they are or how scattered and random and crazy they are. Third trend is that reactions that make more molecules increase entropy. So here's an example of, what is this, nickel oxide. And we got 2 molecules of that. It decomposes to form 4 nickel atoms and 3 oxygen molecules. You start with two things, you end up with 7. So now these 7 things can be spread out anywhere. Whereas before, you had 2 things. And if you knew where one nickel atom was, you knew where a second one was. It was attached to the same molecule. And you have a pretty good idea where to find 3 oxygens because they're also attached. So knowing where 1 nickel is, you got a good idea where a second nickel and 3 oxygens are. But after the reaction, if you know where 1 nickel is, you have no idea where the other oxygens are. They're separate molecules and they could be anywhere. Yeah, so by increasing the number of molecules, you increase the disorder, the randomness, or the potential to be random, right? They can be all over the place. Lastly, this is the one you're probably more familiar with when you think of random. Anything that just makes things more randomly arranged is increasing the entropy. And the first thing I think about is a deck of cards, right? So if you line up all the cards in order, according to the suit, that takes some energy, it takes some time, it takes some effort. You can throw them up in the air and they just go everywhere. And very easily, nature says, let's increase the randomness. Let's increase entropy and just scatter them and mix them up. That's a more favorable, more usual arrangement of those cards. So that's increasing the entropy of the system by mixing them. Okay, I think that's the end of this column. Let's go up here and see what else we got. Well, let's talk about predicting spontaneity. So we said you had to know both enthalpy, heat of reaction, exothermic mainly. You also had to know entropy, randomness. We want it to increase, at least nature wants it to increase. And let's put them together so we can predict spontaneity. And so here's the outcome. Here's the equation that works. You don't have to memorize it. I'll give this to you. But you calculate something called the free energy. Simply said is you find out what is the value of your heat of reaction, find out the value, it's a number, for the measurement of how much the entropy is changing, multiply the entropy times the temperature, and change the sign, put those two together, and you get a new number called the free energy. And if the free energy is negative, it's spontaneous. Cool. A couple things to be aware of. This equation only works with temperature in Kelvin, so not degrees Celsius or centigrade, and not in Fahrenheit. So I haven't been using Fahrenheit. I might give it in Celsius. The homework typically does. So you have to use the equation, the Kelvin scale for the temperature. When giving the Celsius, simply add 273. Again, that's not something you have to memorize, just something you'll use. Cool. So this will be a math problem. You'll be given values of delta S, delta H. You'll be told what the temperature is. It might be in Celsius, you'll have to convert it. And then just do the math. Find out, does the delta G have a negative sign in front of it? If so, yay, it's spontaneous. I had some students tell me this as a way to remember, when is delta G negative, spontaneous? So, sorry. When is a reaction spontaneous? It's when delta G is positive or negative, I forget. Someone told me once that for most people, something spontaneous is not a good thing. Like a car accident, or if someone sneaks up behind you and surprises you, that's spontaneous. You scream, or you might even cry, or get really mad. It's usually a negative response. So most things are spontaneous, people respond negatively to. That's a good way to remember that when delta G is negative, that indicates a spontaneous reaction. If it turns out that your calculations show delta G is positive, then it's not spontaneous. But in fact, if you go backwards, if you reverse the reaction, that one is spontaneous. So go back over here to this example. We said, hey, put some methane and oxygen into a flame, it's spontaneous, it'll keep on going. If you try the other reaction, reverse it, it's non-spontaneous. So if we had the numbers for delta H and delta S, we would do the math and discover, hey, for this last equation, delta G is positive. And it says this, if it's delta G is positive, then it does not work by itself, it's not spontaneous. But if you take the products, put them on this side, take the reactants, put them on that side, you then create a spontaneous reaction. That's this one. So if you reverse it, the reaction will be spontaneous. That's powerful. So that's a great way to predict whether or not reactions are spontaneous. There's one more case. Though unusual. What happens if delta G is neither positive nor negative? What if it's equal to 0? Well, it simply says that both the forward and the reverse reactions are possible. Why does it say non-spontaneous? Because I cut and pasted and forgot to correct. The reaction process is spontaneous in both directions. That's what it says right here. Both forward and reverse reactions are spontaneous. Let's look at some examples. I got an example of each one right here. Excuse me. So I decided to pick something that you probably already know the answer to, but we'll do the math to verify it. So will water melt spontaneously at 10 degrees Celsius, 0 degrees Celsius, or negative 10 degrees Celsius? And well, you already should know. When does ice melt? Wow, got lots of errors here. Sorry. Well, ice melts spontaneously at 10, 0, or negative 10. Well, at negative 10, that's when water freezes. At positive 10, yes, you're above the melting point or the freezing point of 0 degrees Celsius. So this is when it melts. This is when it freezes. And 0, that's the temperature which if you're cooling it down, it'll freeze. And if you're warming it up, that's the temperature where it will melt. But let's say we didn't know the answers and we only had the delta H value and the delta S. Does it make sense that these are both positive numbers? The process we want is taking solid water, which is ice, and making it liquid water, which is water. And it says here the heat of reaction is a positive number. Okay, does that mean it's exothermic or endothermic? It's positive. Well, be the reaction, you be the ice cube, and you're solid changing the liquid. What are you doing with heat energy? You're sucking it up. You're absorbing heat energy so you can melt. And if you're absorbing, it's going into you, entering you, it's endothermic. And yes, that's a positive value. You're taking on more energy, building up more energy is a positive quantity. Yeah, that makes sense. Delta H should be positive for melting ice. Delta S, that's a positive number too. Does that make sense? Well, delta S increasing positive number means you're getting more disorder, more random. Is that happening? Yes. We're starting with something solid, nice neat array of all these water molecules frozen in place, and we're making them liquid. Now they're bouncing around in the liquid puddle. They can be anywhere in that puddle. They're not neatly arranged into a crystal of a crystal of ice. So yes, that makes sense. Going from solid to liquid, you increase the randomness. Increasing means it's a positive delta S, positive change in entropy. Cool. Okay, so those numbers make sense. Okay, so we're going to try, let's try 10 degrees Celsius. And then remember, we have to add 273 to it to make it 283 Kelvin. And our equation is delta G equals delta H minus temperature delta S. And we want to verify that at 10 degrees, delta G should be negative because we already know ice does melt at 10 degrees. Let's find out if the math works. So H is 1,440 calories per mole minus the temperature. We just did that, it's 283 Kelvin. And then delta S is next. It's over here. It's 5.26, and the units are calories, moles, times Kelvin. I know, 3 units for that. Why is that? Well, because we have to multiply the entropy times temperature, and that cancels out the Kelvin. And then afterwards, we have calories per mole, and enthalpy is also calories per mole. So the units match, so you can add them together. And the free energy then will be calories per mole. So we're all good. Let's do the math. 1,440 calories per mole minus, get the calculator out, 283 times 5.26. You know what? I'm supposed to be at 27. Sorry. Man, I gotta check my my slides before I start making a video. That should be 5.27. And 10 degrees, I got 1490. I rounded off to 3 sig figs. I know you're not supposed to do that, but I wanted these numbers to come out nice. So this is a negative 50 calorie per mole. And for you and I, the 50 is not so important. It's that negative sign. And we realize negative delta G means spontaneous. Yay! So if you didn't know it, ice melts at 10 degrees. Okay, at least the math works. Let's try it at 0 degrees. That's 273 Kelvin, right? That's a nice math problem. The temperature Kelvin is equal to Celsius plus 273. And if the Celsius temperature is 0, then Kelvin must be 273. Delta G equals delta H minus temperature delta S. Delta G is 1, well, let's see. H is 1440 minus 273 times S, which is 527. I'm dropping the units because we already checked. We're only changing the 283 to 273. So we know the units are going to end up in calories per mole. And if you do this math, multiply that out, I got 1440 minus, and this number, oh, the 3 sig figs, guess what? It's also 1440. That equals 0. And that says both forward, when delta G equals 0, both forward and reverse reactions reverse. Reactions are spontaneous. So what's our reaction? Well, the solid going to liquid. So forward is solid going to liquid, and the reverse is liquid going to solid. At 0 degrees C, which is 273 Kelvin. Does that make sense? It actually does. So if you're at 0 degrees, that's both the melting point, that's what this equation is. That's the melting point. At 0 degrees, ice turns to water. But at 0 degrees is also the freezing point. That's a temperature where liquid water becomes ice. Both reactions can happen. And it really depends on the net flow of energy, right? Are you trying to raise the temperature above 0, or are you starting to lower the temperature below 0? That'll decide which of these are going to dominate. But if you're right at 0, keeping it steady at 0 degrees Celsius, you can freeze and melt at the same time. Next time you have a really cold drink on a cold day, I mean, if you get your kitchen down to 0 degrees Celsius and get a nice glass of ice water, watch the ice cubes. It's going to be hard to get that cold temperature. You will see that portions of the ice will shrink as it melts, and other portions of ice will actually expand or grow as ice cubes are both moving forward and reverse. As long as you got the temperature at 0, both are spontaneous, both can occur. Kind of crazy, but it's true. All right, let's go to the other one. We're going to go that the temperature is a negative 10 degrees. And we had 273, sorry, Kelvin is 10 degrees Celsius plus 273, and that's 263. Let's find out if for the reaction, solid going to liquid, right? That's what these numbers are for up here. Going from a solid to liquid, it's endothermic. The ice wants energy to melt. Let's see if that's a spontaneous process at negative 10. So delta H minus T delta S is 1440 minus 263 this time, and 5.27. 1440 minus 1386. And that gives me 54 degrees. More importantly, it's a positive. On your exam, you don't have to put the plus sign, but it helps, right? That's the most important feature here. It's 54 calories per mole. Units are nice too. But again, the positive sign, delta G, is positive. So not spontaneous, or the term is non-spontaneous. But reverse is, reverse, spelled with a V first, reverse is spontaneous. So the reaction we calculated for was solid. Are you changing the liquid? No, not at minus 10. But the reverse is liquid will change to solid. Yeah, water freezes at minus 10 degrees Celsius. Cool. Okay, that's plenty for now. I'll see you in the next video.